All right, so last video we talked about how to use annihilators and the concept of particular solutions to solve non-homogeneous linear differential equations. Last time we talked a lot about using this usual trial solution as your way out of doing a lot of work and just solving the system pretty easily. We saw that the most difficult part was actually solving for the coefficients involved towards the very end. And so I want to just cover now what happens if the usual trial solution fails. So if you'll notice in this middle column of the table here, there's a condition. Each one of them starts with if. So if something, then go through and use that particular solution. If that fails, then you have to use a modified trial solution, but it's not exactly trivial as to how you do it. So I want to cover it real quick. So what happens if the usual trial solution fails? Well, so as an example, let's check out y double prime plus 3y prime minus 10y is equal to 14e to the 2x. Okay, so what you'll notice is we won't know if the usual trial solution fails until we get to that point in the problem. So we continue solving as we normally do, right? So first of all, what we have to do is we have to find our complementary function here. So we have to solve the homogeneous differential equation. So what we do is we'd say y double prime plus 3y prime minus 10y is equal to 0. We factor this down in terms of differential operators, like so, which gives us an auxiliary polynomial that looks like this. So we factor this auxiliary polynomial down. We get r plus 5 and then r minus 2. So we know our solutions here. Y1 is going to be e to the negative 5x, and y2 is going to be e to the 2x. So our complementary function is just a linear combination of the two of them. Great. Okay, so that's part one. Part two is we need to guess a trial solution, a particular solution y sub p. And so if we go up and we look at the differential equation we have, our outside function is 14e to the 2x. All right, so we go up to our table and we look at the appropriate function on the left-hand side, all the way in that column. If you look at the second table, it looks like the very first row there. So we have some constant times e to the 2x. So the usual trial solution says that if the polynomial differential operator evaluated at a is non-zero, then you use that normal particular solution. So let's check that. Is p of 2 equal to 0? Because 2 is what our a value is in this case. And we go up and we look, and this is p of d. P of d factors to d plus 5 and d minus 2. So when we plug 2 into there, we do indeed get 0. So p of 2 does give us 0. Is that a problem? Not necessarily, but we know we can't use the usual trial solution. So that's out the window. We next move over into the column on the right-hand side. And it gets a little tricky from here. But what it's saying now is you don't use the particular solution they gave you. You use something with x's involved now. So what this is saying is if a is a root of p of r is equal to 0, so we found it is a root, with multiplicity m, then we try a new particular solution. So try y of p, and I'm going to write it exactly how it is down in the table, and we can talk about the parts. A naught x to the m e to the 2x. Okay? Now what's really tricky here is this m, because m is the multiplicity, as the table says, of that particular root. But notice that it's not the multiplicity in total. It's the multiplicity of like pretty much the problem that we have with it here. So that was a horrible way of explaining it. But, with multiplicity, we'll see, we have a 2 root here, and we have another 2 root here, but our multiplicity is not equal to 2 here. Our multiplicity is equal to 1, okay? So if, you have 14e to the 2x is f, then you have this 2 show up one more time, so m is equal to 1. They did a horrible job of explaining that in the thing here, because, when you think of multiplicity, you think, hey, it shows up twice. I need to put a 2 there, but you don't. You put a 1, and I'll try to relate that back in a second. But m is 1 here, and so our particular solution is going to be a naught x e to the 2x. All right. So let's do a little bit of a digression. So why can't we guess the original guess? I'll call it what it actually is, the usual trial solution. Was just this. It was just a naught e to the 2x, okay? So you might be asking, why can't we actually guess this? And the reason being is this entire thing right here already shows up somewhere in our equation, shows up here in our complementary equation, okay? So if it shows up there, then what that means is that every function that's of this form here gets sent to 0 because it's involved in our complementary function. We know that the complementary function, by definition, is the solution to the homogeneous differential equation. So I know that any linear combination of these will solve this equation here. So I know that if I plug just a naught e to the 2x in, it will get sent to 0, and I will not have a way of getting that f out on the right-hand side if I choose this to be my particular solution. So what I need to do then is I need to choose a different one, and it tells me exactly which one to pick. I need to use this one, all right? What I want to talk about now, though, is why this x shows up here, because this looks a little familiar. The concept of adding an extra x in when something goes wrong. So this looks familiar. And I want to talk a little bit about why it shows up here. So we're going to do a quick digression back into the last video. And remember what we're doing in the first place. Okay, so we had some linear differential operator applied to y, and it gave us f. But we didn't want f, we wanted 0, right? Wanted 0. So what we did was we applied what we called the annihilator to both sides. And that's how we were able to get this 0. So what you'll notice then is that in our particular case, L of D, if we just scroll up to where we found it, is this thing, same as P of D, is equal to R plus, not R, sorry, D plus 5, and D minus 2. But what you'll see and what we kind of have left out here is that the annihilator that actually goes on this side is equal to D minus 2. So this is just in the textbook. This is the differential operator you apply to 14e to the 2x to get it equal to 0. And so then our actual left-hand side here just becomes D plus 5 and then D minus 2 squared. And so we saw when we had roots that repeated, so if I factor this out, my roots would be -5, and then r is equal to 2 repeated twice. We saw when we had repeated real roots that our solutions were going to be equal to e to the 2x, and then we needed to, for some reason, add in this x here, e to the 2x. And so what we did here then, to the -5x here, we have this solution here corresponds to our complementary function, and then this one here pops out as the solution, as our particular solution here, okay? This is where it comes from. Just I wanted you to be familiar with why we stick this x in here in the first place. It just is because we end up with kind of a repeated root. That's all. And so then what we can do is we know what our particular solution is. So y of p, I'll write it one more time since we digressed a bit, is a naught x e to the 2x. And so I need to solve for a naught. So what I do, I plug a naught x e to the 2x into my differential equation, y double prime, what was it? Plus 3y prime minus 10y is equal to 14e to the 2x. So I take two derivatives. It would make sense, first of all, to just write it like this, I think. A naught x e to the 2x yp prime is equal to a naught e to the 2x plus 2 a naught x e to the 2x. That's just one derivative, and then we take another derivative. The first term stays the same with an extra 2 that comes down. And then this last term becomes 2a naught e to the 2x plus 4a naught x e to the 2x. Okay, so if we add all of these together, y double prime is 4a naught e to the 2x plus 4a naught x e to the 2x. I add to that 3 times y prime. Y prime was a naught e to the 2x plus 2a naught x e to the 2x. And then I subtract off of that 10 times my particular solution here, which is a naught x e to the 2x. Okay, and so we have two different types of terms. We have terms with an x, and we have terms without an x. So we can group those like terms across the equal sign, or we can group them all together first. So the ones without an x, we have 4 of them here, and then plus 3 of them here. So I have 7 a naught e to the 2x. And then what's actually cool here is you get all of the terms with the x to cancel out on this left-hand side. So you'll notice that if there was, for instance, this is just as an example, if there was a remaining term here, just like, I don't know, 3 of them that showed up still, remember, we're setting this equal to the outside function they gave us is equal to 14 e to the 2x. You'll see if there was terms left over, the only coefficient we have here is a naught, but you'll notice that we have to set a naught equal to 0 because there's no terms over here that have x e to the 2x in them, right? So I'd have to equate my coefficients. I'd have to say that a naught is equal to 0. And then I would just, be back to where I started. Nothing would be helpful at all. So what's really cool here is that if you have a case like this, these will cancel out. And you will be able to solve for a naught just based off of the terms you need here. So this was if that were to happen. Remember, it's not actually what happens. We get this term left here, and then you can easily solve for a naught. And so a naught is equal to 2. That tells us that our particular solution is equal to 2e to the 2x, 2xe to the 2x. And so our general solution is going to be our particular solution plus our complementary function. Our complementary function was all the way up here. We have c1e to the minus 5x plus c2e to the 2x plus 2xe to the 2x here. And this is your exact solution. So in this video, I wanted to keep it short, and I wanted just to show you what happens if you get something that does not work with the usual trial solution. Don't freak out or anything. As we saw here in the little digression we had, it actually makes sense to us what pops out in this modified trial solution. And so, yeah, this is pretty much what you have to do. You hope the usual thing doesn't work out, but if it doesn't, you should be comfortable with the modified trial solutions as well.